Okay, so the product and quotient rules are the other two techniques that you can use to differentiate more functions. So the product rule looks like a product. That's exactly what it is. Product, don't forget, is a multiplication. So we're looking for the cases where we can see two functions multiplied together. We can represent that with f of x and g of x as a function, like I've got written down here. In which case, the derivative, dy by dx, is the first function multiplied to the derivative of the second function, add the second function multiplied to the derivative of the first function. We could use sort of new parameters, so u and v, much like we do with the chain rule, in which case dy by dx is u v prime add v u prime. So it's a little bit neater, but it's saying exactly the same thing. Quotient, well, quotients tend to be to do with fractions, so we're looking for fractions here. So when you've got one function stacked on top of another one, again we'll use f of x to represent the first fraction and g of x to represent the second fraction. We could also use u and v again. Okay, the order is really important in this one. So when we go for the derivative, we're going to do the denominator fraction first. So g of x multiplied to the derivative of the second one. And the reason the order is important is because we've got a minus sign there rather than an addition sign. So minus f of x g prime of x, so the derivative of the second, all over the denominator function squared. If you're using u's and v's instead, we're doing v du by dx, or u prime, either one of those notations, minus u dv by dx, all over v squared. So just a reminder, these notations, the v prime and dv by dx, those mean the same thing. They're equivalent to each other. It just depends on the notation you're using, whatever suits you. But do make sure you've got the right bits in the right order there. So in the product rule, they can go either direction. You could start with f of x g prime of x, or start with g of x f of x. Because there's an addition sign in there, and addition is commutative, it can be done in any order. However, the quotient rule has that minus sign in there, and that means that we have to have things the right way around. So we're going to start with the denominator function g of x, or v if that's what you're notating it as. So let's look at an example of the product rule, and I'm quite particular about my layout, so I'm going to insist that if you are my student, you are also being particular about your layout. I would always first quote, I guess, the structure, really. That's what we're trying to say here. So we're saying I'm looking for the case where I've got some function u multiplied to some function v, and now I can assign functions to u and v. So I can say y equals u times v, where u is x to the power of 4 and v is 3x plus 2. Now we can clearly see these two things are multiplied together. There is a product there, so in order to find the derivative we will use the product rule. Okay, differentiating both of those using any notation you like, as long as it's consistent and proper. Du by dx then will be 4x to the power of 3, and dv by dx will be just 3. So just simply differentiating each of those functions individually. Now the product rule tells me that dy by dx, the derivative of the original function here, is u dv dx plus v du dx. Quote the formula, you start to get it into your brain, you don't have to think so much about holding all these pieces of information in your head. And now, I'm just running out of space on my board, so I'll just squish up here. Now we just simply plug in the bits that we've got. So I know that dy by dx is u, which is x to the power of 4, dv by dx, which is 3, plus v, which is 3x plus 2, times by du by dx, which is 4x cubed. Now I need to sort this out. It is not acceptable to leave it as it is, mainly because it's a hideous mess, but there we go. We've got 3x to the power of 4, and I'm going to multiply out these brackets just for a minute, just to see what I've got. Actually, no, do you know what? I'm not. I'm going to just leave that 4x cubed there, then 3x plus 2. I'd like to be able to factorise, mainly because if I'm going to end up having to find stationary points or the locations of various I don't know, gradients or something like that, a factorised form is probably going to be most useful for me, particularly with stationary points, because then I've just got multiplication equaling 0 and either one of my parts is equal to 0. So I need to make that factorisation. And I need to think about, right, okay, what is common to both of those factors? And x to the power of 3 looks like the most that I can pull out. So let's pull the x to the power of 3 out. Now, to this first term here, we are left with 3 and x, in the sense that if I was to multiply that x cubed back in, I'd get back to 3x to the power of 4. In the second term, pull out my x cubed, I'm left with 4 lots of 3x plus 2. And I don't think I can do anything more with that. I should now just be able to simplify that bracket though. So I've got 3x add 12x add 8, which is 15x plus 8. And I can't put any other factors in there, so I'm all done. Most people actually find that factorising right at the end the hardest bit. And it's because you end up with things like this. To the power of minus 1, add 2 lots of x. That's 1 to the power of... Oh, let's try and keep it the same thing, shall we? You end up with things like this, and it can be quite difficult to think about what you're actually going to pull out. So just say this is our derivative, for instance. We've got x plus 2 to the power of minus 1 plus 2 lots of x plus 2. And I want to factorise this. So I want to pull it into things that are multiplied together rather than leave them as additions. I can clearly see there's some sort of x plus 2 in both of these factors here. So there's an x plus 2 to the power of minus 1 and just as x plus 2, and that of course is to the power of 1. So how am I going to pull this out? Well, in all cases where we factorise, we pull out the lowest power that's common, or rather the highest power, but the one that's common to both things. So that ends up being quite low. So I'm going to pull out x plus 2 to the power of minus 1 here. So I think that's the most useful thing. What am I left with? Well, I'd need just a single 1 there to get back to x plus 2 to the power of minus 1 from my expanded term. In the sense that if I just multiply those two together, I get back to this thing here. But what about the other one? Well, I know I've got 2. That I haven't pulled that out. I can't do anything with that. But what would this need to be in here so that I would, if I was to multiply it by x plus 2 to the power of minus 1, get back to x plus 2 to the power of 1? Well, we know that when we multiply the same bases, we add the powers if we're multiplying. So I'd need to add something, add minus 1 and get me to 1. That something obviously is 2. So x plus 2 squared needs to go in that bracket. Don't believe me? Expand both things out. X plus 2 to the power of minus 1 times 1 is x plus 2 to the power of minus 1. That's that bit good. X plus 2 to the power of minus 1 times by 2 x plus 2 squared is 2x plus 2 to the power of 1. So I've factorised that out. But that is definitely the trickiest part, and this just requires some good bit of practice. I don't even know if I spelled practice right, who cares. The quotient rule then, same idea, set it up, make sure you're very particular about your layout, plug things into your formula, and any cancelling, simplifying, that kind of thing you can do, all good and well. So we're going to set this up. I'm going to use f and g notation here, so function notation. So I'm saying, okay, I've got a function that is y equaling something over something else, where, and now I can assign my functions, so f of x is x cubed, and g of x is 2x squared add 1. Differentiating both of those then, so f prime of x is 3x squared, apparently can't differentiate today, and g of x is 4x. Now, the formula tells me that the derivative of this function, if it's in this form, is g of x f prime of x minus f of x g prime of x all over g of x squared. Don't forget the order's important here because of that minus sign. Okay, so plugging everything in then. dy by dx is g of x, 2x squared add 1, times by f prime of x, so 3x squared, minus, where are we? There we go, x cubed times by 4x, all over 2x squared plus 1 squared. Okay, we could do a little bit of a sort out, I think. Possibly, we might not find that much that cancels, but we can still sort stuff out. So that will give me 6x to the power of 4 add 3x squared minus 4x to the power of 4. Not sure anything is going to cancel, but we'll keep going and persevere, see what happens. That's 2x to the 4 add 3x squared over 2x squared add 1 all squared. I could factorise the top, I guess. Pull out an x squared, so x squared leaves me with 2x squared add 3 over 2x squared add 1 all squared. I can't simplify anything down, but that's absolutely fine. I've left it an a factorised simplified fraction, so we're all good there. So we can use these rules in the normal ways. If we are differentiating, the things that we could be asked to do are find the location of stationary points, and their nature, so are they maximum, are they minimum? We know that that's when dy by dx equals 0. The process after that point is exactly the same. It's just getting to that dy by dx. I might have needed to use the product or the quotient rule, or of course the chain rule that you've seen in a previous video. I could be asked for the equations of tangents or normals, which you've been doing since C2. Don't forget, your tangent lies with the same gradient, your normal lies with the perpendicular gradient. Something that people forget over the summer, I don't understand it. Yeah, so it's all the normal stuff. You could find gradients at particular points or particular points where there is a given gradient, all the stuff that you'll have seen in C1 and C2, but just with these new techniques just to get to the differentiation bit.